Okay, so I'm going to wrap up the third part here of 2-3 notes for the second chapter here. Without using specific numbers, how can you determine the horizontal distance an object would travel if lodged at some angle and allowed to return to the same height? So they don't want us to use specifics, they want us to do this generically and basically generate an equation representing the horizontal distance. So I'm looking for really my delta x, right? And I know the only relationship I'm using delta x would be Vx equals delta x over t, because my horizontal velocity would be constant. Well, the key here is if I'm launching something at an angle, right, I don't know its velocity, I don't know its angle, but in terms of those two unknowns, I could define this horizontal component as v cosine of theta. So then v cosine theta equals delta x over t, right? And then again, I'm looking to solve for delta x, so delta x equals v cosine theta times t. So at this point, I run into a little bit of trouble here because obviously I have a lot of unknowns, but if I look at my vertical measurements, so now I'll start considering my vertical measurements, well, I know my initial vertical velocity would be v times sine of theta. I know my acceleration, as always, would be gravity, right? So I may just call that negative g. In this case, negative because it's going downward and my velocity is going upward. And then the key here is choosing wherever we want to break this up. So if I choose to break it up at the top, I know my final velocity at the top would be 0, but my time would actually only be 1/2 of the time that it originally took, right? So then setting this up, if I just use my velocity as a function of time, if I use VOTAT, I can set up an equation with similar variables to ones I've already used. Specifically, I can do v sine theta, 0 would be my final velocity. So 0 equals v sine theta minus g times, again, 1/2 t. So at this point I've got two equations, but those two equations are represented in many of the same variables. I've got t, I've got g, I've got my velocity here and my theta. So what I'm going to go ahead and do then is, just to help us illustrate this, I'm going to go ahead and solve this for t and then substitute that into this equation. So in solving this for t, well, I'd add that 1/2 gt over. So I get 1/2 gt equals v sine theta. And then I get t equals, really I'd multiply both sides by 2, so 2v sine theta over g. So again, that's what I end up with for my time. Now I'm going to go ahead and just take that time and substitute it into my other equation. So I'll take this entire chunk here for the time and plug it in over here. So what I end up with then is delta x equals v cosine theta times 2v sine theta all over g. And obviously I can clean this up a little bit more here. If I do clean that up, what I'm actually going to do is I'm going to go ahead and bring the v's out front together. So I get v squared. And then I'm going to rearrange this so that I've got 2 sine theta cosine theta. I've got 2 sine theta cosine theta. All of that over g. Well, the reason that I did that, the reason that I chose to specifically arrange it that way, is because if you actually remember going back to your trig identities, this is a special trig identity. 2 sine theta cosine theta is actually sine of 2 theta. So what that tells me then is delta x really equals v squared times sine of 2 theta all over g. So this is actually pretty helpful, because if I ever want to find the horizontal distance of a shot, all I have to know is the actual velocity, the acceleration due to gravity, which we assume we always will know, and then theta. So I really only need those three measurements, and I can solve for the horizontal distance of the projectile. The other reason that this is very helpful here, so the other reason that this expression is helpful, is we can think about when would we have the maximum distance, when would delta x be the greatest. Well, delta x would be the greatest whenever sine of theta is the greatest, right? Assuming I keep the velocity and the gravity the same, if I want delta x to be as big as possible, then I want sine of 2 theta to be as big as possible. Well, sine of 2 theta, sine is a function that is at its largest when it's sine of 90 degrees, right? Because we know that at sine of 90 it's equal to 1. So what that tells me then is sine of 2 theta would equal sine of 90, or in other words, right, 2 theta would equal 90. So this projectile is going to go its furthest when theta is 45 degrees. Now most of us probably already assumed that fact, but this actually mathematically proves that in the absence of air resistance, if we're firing a projectile and it's landing at the same height, then it's going to go the furthest when it's projected at 45 degrees. The other reason this is helpful is it shows me that two complementary angles will have the same range of motion. And this summarizes nicely on the next page here. Okay, so basically, again, just reaching from that conclusion. The maximum range is going to be achieved here when I'm at a 45-degree launch angle. But I also want you to notice that when we launch at 30 degrees or 60 degrees, notice they take very different paths there, but both times they go the same horizontal distance. The same thing with 15 degrees and 75 degrees. And the reason for that is if I'm looking again at my sine of 2 theta, well, if I were to look at, for instance, the 15 and the 75, sine of 2 times 15 would be sine of 30, and sine of 2 times 75 would be sine of 150. And if we're thinking about our unit circle, we know that the sine of 30 and the sine of 150 are the exact same measurement because they're at the same altitude, they're at the same height, right? The y values are the same. So we know that those two are the same, which is why these two complements travel the same horizontal distance. So it's actually a very powerful conclusion for us. Again, going back to that equation that we solved for here. It simplifies the situation a little bit more, and it allows us to kind of make some generalizations that help us in answering some of those more difficult questions. So anyway, good chance to kind of summarize again. If I want the longest distance, I'm going to project it at 45 degrees. However, if I project it at either 30 degrees or 60 degrees, assuming there's nothing in the way, those two will reach the same horizontal displacement. So again, a pretty interesting, pretty powerful fact. The last example then in these notes, actually not too bad, so I would encourage you guys to try and work through this. You've actually seen this before if you've taken the Physics 1 curriculum as well. So anyway, baseball player hits home run and lands in the seat 7.5 meters above the point at which it was hit. It gives us that final velocity, ignoring air resistance. Find the magnitude and the direction of the initial velocity with which it leaves the bat. So again, the context here, the ball's hit, it travels upward, travels upward, travels upward, and then lands some height, 7.5 meters above where it was hit from. And then they give us the velocity at that location. Well, again, I would encourage you guys to try this on your own. I think if you work together, you can definitely work your way through this. So I'm not going to work this all the way out just to save a little bit of time here. But if you are stuck, if you do need a little bit of help, right, find your components, find your x and your y components. At the end here, we know that our x component is constant the whole time, so we've already got that. So then you would just need to find your initial vertical component. Well, you're looking for your initial vertical component. You can find your final vertical component, and you've got your change in y of 7.5 meters here. So you can find this, you've got this, and then as always we've got our acceleration of negative 9.80 meters per second squared. So it's just a matter of calculating that initial vertical velocity and then finding the hypotenuse and the angle. So again, I'll leave that to you guys to try and finish that out, but hopefully the rest of this section wasn't too bad.